Okay, hello everyone. I am Somik from ISS Cultivation. So this video is not about NEB theory. It is about how VC-NEB actually works in VASP and what files actually matter. I noticed that while NEB is discussed in many places, okay, but a complete VC-NEB workflow in VASP is almost never shown on YouTube. So in this video, I will walk through a real VC-NEB calculation, focusing on what actually matters for DFT users. Okay, for to understand the theory, I should prefer this paper. Okay, you can just go through this paper to understand the theory, basic theory. We all DFT users know that NEB finds the minimum energy path between two structures while keeping the cell fixed. But VC-NEB extend this idea by allowing both atomic positions and lattice vectors to evolve. Okay, I want to reproduce the result from the paper named Pathway Towards the Ferroelectricity in Hafnia. Okay, they mentioned they used North elastic band method, and I want to reproduce this result. This is the P420MC tetragonal centrosymmetric structure of hafnium oxide, and this is the ferroelectric structure of hafnium oxide. This is the polarization is the up direction, and here polarization is the down direction. And they got the energy barrier 40 MeV per atom for this phase transition from centrosymmetric to PCA21 ferroelectric structure. Okay, so this is my hafnium P420MC centrosymmetric structure, and this is the ferroelectric structure. This is the final structure. Okay, so 1 second and scar 1. Okay, you can follow that. Here this is my initial structure, centrosymmetric P420MC space group structure of hafnium oxide, and this is the final structure of ferroelectric structure. You can follow carefully. Here the lattice vectors are different for two structures, and atomic positions are also different. Okay, for this situation we have to use the VC-NEB or variable cell NEB method. Okay, so this is my INCAR file to calculate the VTST NEB VC-NEB variable cell NEB method. Okay, so this is the INCAR text. You should follow this text carefully. Okay, as hafnium oxide is non-magnetic, so I deactivate the magnetic tag. Okay, and for NEB we have to use this type of tag. You can just go through or follow this website, North elastic band website, to understand the role of these tags, and you should just follow VASP wiki. All DFT users know that to understand the INCAR tags properly. Okay, you should follow these tags carefully. Okay, otherwise you will fail to calculate VC-NEB in phase transition cases. And here I have chosen 8 images between my centrosymmetric and ferroelectric structure, so I am setting that images is equal to 8. Okay, I have only 8 intermediate images between centrosymmetric and ferroelectric structure. This 00 and 09 directory should contain the POSCAR file and the outcome of relaxation calculation, and other directories from 02 to 08 should contain the POSCAR file of intermediate images. Okay, so this is my result. This is the reaction coordinate, and this is the relative energies, and this is the forces. Okay, so the paper got energy barrier like this, and they got energy barrier is 40 MeV per atom for centrosymmetric to ferroelectric PCA21 phase transition, and this is my result. Okay, this is my centrosymmetric and this is a ferroelectric structure. And I have also noticed that when atoms are moving in opposite direction, energies are same, energies are degenerate. Okay, so this is my calculation, and you can follow that for energy barrier which here less than 40 MeV per atom. Okay, and in this phase transition case, less energy barrier means more correct, more accurate result. So my result is less than 40 MeV per atom, so my result is more correct than the paper result. Okay, so you should follow this tag INCAR tags carefully. And also I want to mention that you should use VASP version more than 5, otherwise VTST cannot work properly. Okay, so